Well, greetings everybody. I would like to do this problem that you see right here, which I took directly off the assignment on my math lab. But I think before I even get to the explanation of how I would work this, I think some background information is needed. This is very important for the duration of your study of calculus and beyond. Okay, so what I have to say that I hope makes an impression on you right now is that in calculus we treat constants and variables differently. I always have to notice when I'm working with any type of function what's a constant and what's a variable. Okay, so if like take this right here, this is our basic rule for derivatives. The first rule that we learn, it's called the power rule, and it says if you have a variable to a constant power, okay, that the derivative will be that power times the variable to the power n minus 1, okay, the constant minus 1. So just make sure you notice about that the way this rule is intended to be used is that x is the variable in the function. It's where you put the input. It can be many different numbers. X can be anything in the domain of this function. It's no one number, but that power is fixed. It's not going to change. Okay, that's what we mean by calling that power a constant. Okay, so variables can take many different values, but constants are fixed. Okay, even if I don't know what that constant is, if you tell me it's a constant, then I'll treat it like a constant. Okay, here's why I think this is so important. I mean, I guess it's just a matter of fact that it is important in calculus, but if we take science that's closely associated with calculus, like say physics, and we look at just about anything, but let's take an example of Newton's law of universal gravitation. When I start looking at the equation for that, it's all letters, okay, in its given form. I mean, I see some subscripts and an exponent, but you know, G, M, R, you know, and so on, F, those are all letters, and we don't do math with letters, we do math with numbers. Now, among these letters, I would need to know what's a constant and what's a variable, because like I said, we're going to treat them differently. So I look at this function, and you know, it's, to me, like I said, it's all letters. But if I read the fine print, if I learn about how this formula is intended to be used, M1 and M2 are masses of objects, which could be different depending on what the objects are. R is the distance between the center of masses. Okay, so that could be different depending on where the objects are, how far apart they are, and so on. And G is a constant. Okay, so G is not going to change. Whenever we apply this formula, G is going to be some fixed number. But it's M1, M2, and R that might vary depending on the situation. So I think that that's very important to start thinking about things like that. Whenever we look at a formula, we'll get our head wrapped around, what am I looking at? What here is a variable and what's a constant? Okay, so that would be true of this one, because you know, I see A, B, X, and if I read about this and if I understand this function, then I'll know what's variable and what's a constant. Okay, all right, so first lesson though is like, for this rule, you might look at it as a variable base to a constant power. That's the only time you use it. Now, what the variables are can be different. Like for example, in this function, f of r, whenever we write function notation like that, this indicates what the independent variable of the function is. So if I see f of r equals whatever, then I know in that function that the independent variable is r, okay? And the 4 is obviously a constant because that is a fixed number, right? So this rule is applicable, and the derivative, if you needed it, would be 4 times r to the third power, okay? What about this one? This is f of t, so here it's a function of t. The input is t. You plug the number in t. T is the independent variable in this one, okay? And it's 4 to the power t. Now, would this rule apply to this function if you wanted the derivative? So let's see, think about that for a second. I know it has some resemblance to this other problem, which we could work by the rule, but looking at it, this is not a variable base to a constant power. It's the other way around. It's a constant base to a variable power. So even though it has some superficial resemblance to the rule The rule is not applicable. We'll learn a rule for this later though. But this is just like between these two examples, one simple lesson on how when we're given rules or formulas, we have to pay attention to variables and constants and where they are, what role they play in the formulas, and also how we apply that to any given problem. Okay, so you see the difference between all that. Now, let's, with that in mind, solve this one. So this says g of x, so I know immediately that in that function, x is the independent variable. X is the variable. And then it says here, just for clarity, that a and b are constants. I don't know what they are. You know, it might be nice if I just see 4, and that's an obvious constant. But like with, say, a lot of formulas in the sciences, maybe the constants are written in the formula, but they're not expressed. Okay, we could look up the gravitational constant if we wanted to. All right, it's a constant, it's a fixed number, but it is complicated, and for that reason a lot of the constants just go unmentioned in the formulas in the mathematical sciences. All right, so we'll just accept g is a constant, we'll do our work, and then later for calculations we might plug in this number. But when we look at the formula, what do you see there? You see g, you see a letter, but you know it's a constant because it was explained that way. Okay, so here I look at this one like that. I say, okay, x is the variable. If I see a, it's a constant. If I see b, it's also a constant. Okay, now beyond that, if I'm finding the derivative of this, I would have to use the rules. Okay, here they are as we're learning them at the moment. This is the power rule that I just explained to you a little bit about. This says if one function is the sum of two others, then the derivative is the sum of the derivatives. If we have a constant coefficient of a function, a constant c times f of x, we carry that constant into the derivative. The derivative of a constant all by itself is 0. And then there's the product and quotient rules. So, you know, in this video, I'm not going to explain all of these rules on their own. I have that elsewhere. That's in other videos. But I'm going to use these rules, okay, with the understanding that a and b in this formula are constants and x is the variable. Okay, so let me, in order to find the derivative, I'll do a little rewriting. So let's say g of x. I don't have a problem with a to the b power. I don't have a problem with x to the 2b power, but the rules apply better and look a lot more like what we have if I write 4 times x to the minus a power. Okay, so I'll make that one change to it. Now what I notice about this beyond that is that a to the b power is a constant. Okay, and then these two are variable bases to constant powers. Alright, so that's what I notice about it. That's the kind of thing I would need to notice about it in order to apply the rules correctly. Okay, now I say that because I think we would be tempted to solve a to the b power by bringing the power down and subtracting 1, because we have a rule that says that you do that. Alright, but that's for a variable base to a constant power, and that's not what we have here. If a is a constant on its own, and if b is a constant on its own, then a to the power b is a fixed number. It's also a constant. Okay, so that entire term is a constant. And its derivative is 0, because the derivative of a constant term is 0. Alright? I carry down the plus. The rules say I can carry down a plus or minus in my work of finding the derivative. I carry down the plus. So what do I do here? This is a variable base to a constant power. I bring the power to the front as a coefficient. I subtract 1, and that's all I can do there. I carry this plus down. Also, our rules say I could carry that coefficient down, 4. Then the derivative here of x to the power negative a, I bring the negative a to the front as a coefficient, and I subtract 1, which you're looking at there. That's as much as I can say about it. All right. Now let's simplify this, clean it up a little bit. I don't need the 0. I wrote it there so you could see that that was the derivative of this first term being a constant. I can't do anything to simplify this second term, so I'll just carry it down there. Here I've got a positive 4 times a negative a, so that's minus 4a for the coefficient. And then there's that power again, negative a minus 1. I guess we could leave it like this. In fact, the answer there has it like that. So that's our answer. There's not a whole lot else meaningful we could do to simplify that. The one thing that we might do in some circumstances is that I can put this x back under the bar down there in the denominator by switching the sign of the exponent, by taking the opposite of this. So I can move this x and its power under the bar, but I have to take the opposite of the power. The opposite of negative a minus 1 is positive a plus 1. So I could put it like that, okay? And you might sometimes see it that way, and you should know that it can be written that way too. With all these, just about any calculus problem, the rules and formulas can be complicated enough that there may be more than one way to write the answer. For that, I might show you a few different ways I can write any one answer for any problem that we do. Beyond that, I'll just have to ask you to ask me for help if you need it.